All right, guys, there are 36 students in this meeting, or I think we can start our lesson. Okay, just a quick recap from last lecture. I did discuss with you about the imperfections in solids, and imperfection in solid means that all I did mention to you that all materials in this world, all objects in this world, all of them are not perfect. All right, only in theory everything is perfect. In practical manners, all of them are imperfect. So same goes to defects in the solids. Okay, you have lots of defects, and those definitions are in the slide. You have few definition. You have point defects, impurities in solids, dislocation, interfacial defects, right? And then for today's lesson, I'll be focusing more on specification on composition, specifically for alloys. Okay, specifically for alloys. Remember, alloys is also a defect. You have alloy material, right? It is also a defect in terms of solid solution over here. Okay, impurities in solid. For example, you have iron, all right, Fe, iron. When you add magnesium, iron, magnesium, something like that. Okay, you add foreign material into iron and it becomes impurities. It can be either substitutional or it can be either interstitial. And guys, remember, last week I mentioned to you for you to have a solid solution, you need to obey the law. Okay, not you, the material needs to obey the law. All right, in terms of Rotary rule. Okay, substitutional solid solution, and these are the laws. Okay, just go through, and so this is the one that we have discussed last week. All right, for today I'll be focusing on specifications of composition. All right, now I did mention to you that lecture 1 is about imperfections in solid, right? So you have some part of imperfection in a bulk material. All right, you have some percentage of imperfection in the bulk material, or I can call that as a matrix. All right, let's talk about composites. Composites made of two material, two or three, all right, or four, whatever it is, but it must be minimum two. All right, so as a material engineer, you should know the amount of composition needed to be added into the matrix. Okay, you should know the exact amount of material be added to the material. All right, guys, can you hear me? Is it smooth?
Sir, your voice is a bit laggy.
My voice is a bit laggy. Okay, yeah, I saw suddenly there's some internet connection problem. Hold on, hold on, hold on. Let me clear all the antivirus. Okay, how about now? Is it clear? Okay, all right. Thanks for pointing out. Okay, who was the one who talks to me just now?
Me.
What's your name?
Loa.
Okay, all right. No, it's so good to hear students' voice, rather than typing. Anyway, thanks for your what they call that points. All right, it's better to mute all because I can see some distortion in voice. Okay, now clear, right? Everything is clear, right?
Yes.
Okay, all right. Okay, you can mute your voice, Lua. Okay. can mute your mic. All right. Okay, I'll be continuing now. Let me guess. I stop at composites. All right. So composites, you have two different types of material, minimum two. It can be either three, it can be either four, it can be either five. All right. Tri material, quad materials, and so on. Now, so in order for you to have a composite, as a material engineer, the engineer should know the exact amount of filler material that needs to be added into the matrix material. So your matrix is your bulk material. A filler material is the impurities that you're going to add. All right, the impurities. Where is it? Yeah, the impurities that you going to add into the bulk material. All right. There are two possibilities. One, it does give some enhancement into the intended properties. For example, let's talk about mechanical properties. It does give some enhancement, or it might deteriorate the intended properties. Okay, there are two outcomes. So these outcomes will be carefully calculated and studied by materials engineer in terms of compatibility. Does this impurity is compatible with the matrix? So those compatibilities are out of this topic, out of this engineering materials topic, but I can give you some insights. All right, they'll look at the valence, they'll look at the ionic bonds, they'll look at the availabilities of electrons. All right, these are the points. They look at the atomic size of the material. All right, these are some of the cues that you can use to check for the compatibility of in composites. All right. So for this course, all right, I'll be focusing only on the specific composition, specifications of composition, where there is a slight hint of how much of impurities that is available in an given material. All right. Okay, guys, there are two main terms for it. Please write it down. The first term is weight percentage, WT percentage, and the second term is atom percentage, AT percentage. Please highlight this. Okay, now weight percentage. Okay, guys, before I continue, so you will be focusing more on weight percentage and atom percentage when you are doing your FYP2. All right, especially for the students who are interested to do experimental based final year project. So you need to be well versed with the calculation of weight percentage and also atom percentage. Okay, specifically for students who wanted to do experimental based final year project targeted into material studies, right? Okay, what is weight percentage? Now, weight percentage is the weight of a particular element relative to the total alloy weight. This particular element is what I meant by the foreign material, or where is it? Impurities in solids. Okay, substitutional material. Okay, so this is the definition: weight of a particular element relative to the total alloy weight. So this is the formula: weight percentage. Your weight in terms of mass of element 1 and element 2, total element 1 and element 2, and your mass of your impurities. So mass of your impurities divided by the total weight of the whole element times it 100 will give you weight percentage. Please highlight these and memorize this formula. Next, atom percentage. Atom percentage in terms of numbers of moles of an element in relation to the total moles of the elements in alloy. All right. Before I go further, essentially both are almost the same. Weight percentage in terms of the total weight, atom percentage in terms of the total moles in the material. Okay, and before that you need to find the total mole, right? Number of moles for element. So this is the number of moles for element 1. Number of moles for element 1, the formula is mass in gram divided by atomic weight. Memorize this. For you to find mole, MOLES, the formula is mass divided by atomic mass. And that mass must be in grams. Okay, G, grams, not kilograms. Not milligrams as well. Must be in grams. Okay, please take note. And then back to the business, atomic percentage. So for you to find atomic percentage, number of moles of element 1 divided by total number of moles available in that material. Okay, available in that material times with 100. So you'll get atom percentage of element 1. If you want to go for element 2, Nm2, alright, Nm2 divided by Nm1 plus Nm2. Same goes to weight percentage. If you want to find weight percentage of element 2, you can use M2. Okay, please memorize these. Okay, now, so now you have two main key points for this specification of composition. One is weight percentage and another one is atom percentage. So by having this, having said that you have two key points, you can convert weight percentage to atom percentage to weight percentage over here. Composition conversion. Okay, conversion of weight percentage to atom percentage for two elements alloy. Okay, just bear in mind this is for two elements only, two elements alloy only. The calculation is different for three elements, right? It is just an iteration for three elements. But I won't be covering three elements here. So this is the formula. So you have atom percentage C1, all right? You can use weight percentage C1 times with atom weight A2, second element, divided by weight percentage C1 times with atom percentage 2 part 2 plus with weight percentage C2 times with atom weight A1. Okay, C is in percentage, A is the atomic weight. Memorize this formula, please. All right. Same goes to if you want to find the weight percentage of C2, you want to convert this to C2, you use the ambiguity of it. Okay, C2 A1 divided by C1 A2 plus C2 A2 A1. All right, times with 100. Okay, so this is the specification of composition. The first part is weight percentage, atomic percentage, and the conversion of weight percentage to atom percentage for a two element alloy. Now, same goes to conversion of atomic percentage to weight percentage for two elements. Okay, this is for weight percentage to atomic percentage, and the next slide is for atomic percentage to weight percentage. I will show you some examples towards the end of this lesson so you can understand better on using these formulas. Okay, try to digest this. All right, now, okay, guys. For students who haven't who haven't clicked the attendance, please click now. I have created the attendance poll. Right, I've seen 43 respondents, but there are 45 students in this. Okay, guys. All right, we shall continue now. Okay, now, now example one. Okay, I hope that you don't look at the solution first. Let's digest the question, all right? I'm not facing you, but I'm just advising you don't look at the solution. We just digest the question first, all right? Then you can have a clear understanding and you can learn much more faster than rather than looking at the solution. All right, now let's start. Okay, there's a question. Hold on. So M1 indicates the weight for atom percentage or of the impurities. Yes, depends. Yeah. M1 indicates for the impurities, M2 is for the full total weight. Yeah. Luaweisen. Okay, all right, good. Okay, guys. Calculate the equilibrium number of vacancies per cubic meter for copper at 1000 degrees Celsius. All right. Calculate the equilibrium number of vacancies. Okay. This is impurities of solids. Previous class, previous lecture, the energy for vacancy formation is 0.9 eV per atom. And okay, they say that this is the energy for vacancy formation. Okay, for you to form a vacancy from an atom, for you to form a void, this is the energy required per atom, right? Now, the atomic weight and the density at 1000 degrees Celsius for copper is 63.5. So this is the density. So this is the atomic weight, all right? And then this is the density, 8.4 grams per centimeter cube. So they ask you to calculate the equilibrium number of vacancies per cubic meter, all right? Per cubic meter. So you need to change everything to meter. But the density given here is centimeter cube. Okay, so this is where students make a lot of mistakes during final exam. Okay, you need to change the units. All right, now let's see the formula. The formula is here. All right, point of defects, NV, number of vacancies per meter cube. All right, N is the total number of atom sites, usually per cubic meter, and then you need to use exponential. QV is the energy required for the formation of a vacancy. Okay, just now it states something, right? In terms of EV per atom, not J mole or not J mole, right? So that is QV. And T is the absolute temperature in kelvins. Okay, students, please take note of these units as well. The unit must be in kelvins and not degrees Celsius. All right, please take note of these. Highlight these if possible. And K is your Boltzmann constant. It can be either 1.38 or 8.26, depends on the Qn units. All right. If let's say the Qn units is in J per mole, you need to use this constant. 1.38 times 10 to the power of negative 23. If the given energy in terms of EV per atom, you need to use Boltzmann constant as 8.62 times 10 to the power of negative 5 based on the units. Okay, please take note of these. Let me point out here. Okay, this is for this and this is for this. Okay, all right. Okay, now let's do it. So this is the formula, NV, and the energy they have given in terms of EV per atom. So you need to use 8 point something as given on the constant. Okay. Now, at first you need to find N. All right, they didn't give N. So for you to find N is the atomic weight copper and its density and the Avogadro's number. All right, Avogadro's number is 6.02 times 10 to the power of 23. Okay, usually this number is assigned. Okay, I just want to let you know what is Avogadro's number. Avogadro's number is the number of atom presence in 1 mole of a material. So in 1 mole, there are 6 times 6.023 times 10 to the power of 23 atoms in 1 mole. So first you need to find N, number of atomic sites per cubic meter first. So per cubic meter means you need to find the density, okay, number of atoms times with the density. The density must change into meter cube divided by the atomic number of copper, which is 63.5. Okay, 63.5. Then you have the number of atoms per meter cube. Okay, I'm repeating. All right. First, you need to find N, which is the number of atom per cubic meter. So for you to find the number of atoms per cubic meter for copper is Avogadro's number times with your density divided by the atomic number of copper. This is your Avogadro's number. This is your Avogadro's number. And this is your density converted into meter cube divided by the atomic number of copper. Then you have total number of atoms, total number of copper atoms in 1 meter cube. So this is the value. Okay. So therefore, the number of vacancies at 1000 degrees Celsius, convert 1000 degrees Celsius to Kelvin is 1273. Okay. So equivalent to N is your number of atoms, exponential. QV is 0.9 given here, 0.9. Okay, the energy required for vacancy, and then divided by your K is your Boltzmann constant. You use 8.62 times 10 to the power of -5, which is given here. Which is given here. Okay. Times with your temperature, which is 1273. Then you have your values. So the number of vacancies at 1000 degrees Celsius is 2.2 times 10 to the power of 25 vacancies per meter cube. So you have 2.2 times 10 to the power of 25 voids at 1000 degrees Celsius in a copper material. Okay. Take your time to go through this example. This is just a basic example. Okay. All right, next, example 2. Now, I did mention to you earlier in this lesson that you can convert weight percentage to atomic percentage and vice versa, where you can convert atomic percentage to weight percentage as well. So this is an example for it. Determine the composition in atom percentage. Okay, determine the composition in atom percentage of an alloy that consists of 97 weight percentage aluminium and 3 weight percentage copper. So they wanted to convert weight percentage to atom percentage. Given that aluminium weight percentage is 97 and copper weight percentage is 3. Okay, so copper is 3, aluminium is 7. So this is the formula. You need to find the atom percentage of alloy. Let's say if you want to find the atom percentage of copper first. All right. If you want to find the atom percentage of copper, you need to take the weight percentage of copper times with the atomic mass of aluminum. Okay, so 3 times with 26.98 divided by the overall system, okay, which is the weight percentage of copper times the atomic percentage of aluminum plus with weight percentage of aluminum times with atomic weight percentage, sorry, atomic mass of copper. Okay, weight percentage of copper times with atomic mass of aluminum plus weight percentage of aluminum times with atomic mass of copper. Then you have atomic percentage for copper. Then if you want to find the atomic percentage for aluminum, you need to switch these to aluminum, copper, aluminum, copper, copper, aluminum. Okay, so this is it. For you to find the atomic mass, for you to find the atomic mass of atomic percentage of aluminum, you need to times the mass weight percentage of aluminum times with atomic number for copper and then divided by the whole system. Then you have the values here. Okay. All right. There's one question. Can use 100 minus 1.3. Where is it? No, I don't understand your question. For which example? What do you mean by that? Chan Wai Lok? Yeah, you can use that as well. Yeah. But this is the formula. But this is the formula. Okay. If it translates to the, if you can simplify this, then shouldn't be a problem then. Okay. All right. Chin Wai Lok. Okay, guys. So just a quick recap. All right, just a quick recap. Today we have gone through the specification of composition, which is in terms of weight percentage, atomic percentage, and composition conversion from weight percentage to atomic percentage, and from atomic percentage to weight percentage. All right, this is the formula. This is the base formula. But if you can simplify this, as what asked by Chan Wai Look. Okay, I don't really understand his question, but if you can simplify this, not an issue at all. All right. Okay, guys. Any questions? Any questions? Okay, I just want to share with you one more thing, which is this. All right, all of you can see my screen, right? So this is the method of assessment. All right, I'll be uploading the teaching plan later in the evening, towards the evening. So this is your lab. Your lab will be starting next week. All right, your lab will be starting next week. Everything is online. So for your lab, the allocated marks is 10%, and I will be having an online quiz here in Microsoft Teams. All right, I'll be having an online quiz. Both allocates for 10% as well. We will be having 2 quizzes throughout this semester, and there will be an assignment 20%. Okay. Okay, there's one Lua Wen Zheng. Okay, for assignment, This will be the dates. Where is it? Assignment. Okay. Week 9. Okay. Week 9. All right. I'll be uploading this in Webble so you can have a clear picture for it. Okay. And then test 20%. And your final assessment will be 40%. Please take note of these. So there's a catch here. So I'll be giving you quiz. All right. I'll be giving you a random quiz. Okay, there's some questions. Kung Ji Sheng, I think he means only the materials of 2 types of materials since we know the percentage of material shortcut. Oh, okay, yeah. Only for 2 materials. Now I know he wants to get there's only 2 types of material since we know the percentage of one material. Yeah, because everything overall will be 100%, right? So he's using 100 minus 1.3%, which is 98.7. Yeah, it translates to a correct value. I'm guessing this, but you just use the formula. It's always better to use just the formula only. Okay, because this involves only 2 material, and 2 material must be 100 percentage anyway, right? That is what he means. Okay, so Clement Tingxian assignment, how many person per group? Okay, for the assignment on the grouping assignment, I don't think I'll give you a group assignment. Okay, all of those are individual assignments. Okay, I'll give you a small what they call that topic, so that you can have an input for it. Okay, for example, I haven't set the assignment title yet, but I'm thinking of to come up, each of you should come up with a material based on the applications that I'm going to give you. For example, I will be giving you about 10 to 15 types of application. Okay, any application. It can be cars, it can be household equipments, for example phones, it can be lorries, it can be cutting knife. Okay, you need to select a suitable material for that application, state out all the properties why you choose that material, and discuss about the manufacturing process. I'll be discussing this further with you later when we approach towards that week. Okay, but the assignment is individual assignments. Okay, so okay, the quiz 1 and quiz 2 will be the catch, because the quiz 1 and quiz 2, I'll be letting you know the date when we approach near to the intended date, so that all of you were attending the class. So I just want to make sure that all of you attend the class so that you can get a quiz mark. So make sure you attend the class. Lua Wing Zheng. All right. So guys, don't worry. I'll be uploading this teaching plan later, so you can. Okay, I'll be uploading the teaching plan later, so you can plan for this semester earlier. All right. So guys, any questions? Any questions for today's lesson? So it's quite difficult for me to. It's quite difficult for me to what they call that teach via online. I just want to make sure that all of you can understand this lesson. So all of you understand the lesson clearly, right? Okay, that's nice. I'm happy to hear that. Okay, if there's no question, I can stop the lesson for now. So I'll be seeing you next week for lecture, practical, and also tutorial. Okay. Please make sure that you have signed the attendance. Please make sure that you have signed the attendance. Yeah, 44 respondents. We have 46 students in this meeting. So whoever haven't signed, whoever haven't, what they call that, select yes for the attendance, please do it now. Yeah, tutorial will start next week. Tutorial will be every Friday after this class actually. So next week after this class, I'll be having tutorial.